Hi, everybody. I'm Fiona, and I'm a developer at a company called CipherStash, and they've sponsored me to speak here. And my talk is definitely directly related to what I work on every day. Ruby was the first language that I learned, and I think as most bootcamp attendees would know, it's generally the case. But until recently, I haven't had the opportunity to work with it professionally, but it's been a lot of fun coming back to Rubyland after all these years. The main language that I have worked with is a language called Elixir. Also, prior to a year ago, I didn't know much about cryptography. How encryption worked was a bit of a mystery to me. I'm not a cryptographer, but today's talk is about sharing what I've learned about something called Ruby application level encryption. I guess party. It didn't really work as a conference title and didn't have the same ring to it that Encrypted Search Party did, so hence my conference title is a bit catchier. But more specifically, a encryption scheme called Order Revealing Encryption. I'll also refer to this as ORE throughout this talk. Just what we'll be going through is I'll start with a bit of an intro on some concepts that will help us understand what encryption is, what do we mean by application level encryption, and why querying encrypted data can be challenging. To learn how ORE works, I built a toy ORE library, which I'll demo at the end, and this library is available as a gem, so you also can have a go and play around with ORE in your own time. But one of the first things I did learn about encrypted data is that sometimes it can limit the usability of that data, as in being able to query or search that data becomes a bit more challenging. So consider this table. It's a users table, and it has a email and date of birth column, so there's some personally identifying information there. And we'd use a statement, maybe something like this, where we'd select all users where a date of birth was greater than, say, January the 1st, 1990, and we'd get a record back, or potentially records. But we want to secure that data, so we encrypt it. And we try and run that same statement again, and we get nothing returned. And why is that? So let's break this down. Ruby application level encryption. Let's start at the end. Encryption. Encryption is the process of converting human readable text, which we'll call plain text from now on, into incomprehensible text, which we'll refer to as ciphertext. And that's using a key or keys, and that data can be decrypted by someone who has access to those key or keys. The output of this encryption, or the encryption, can be what's called non-deterministic or deterministic. And non-deterministic means, given the same plain text, a different ciphertext will be generated every time. And we'll introduce the concept of something called an IV, which is an initialization vector, and this is what introduces randomness to our ciphertext. Deterministic means that given the same plain text, the same ciphertext will be generated every time. And there are pros and cons to both of these, which we'll explore in a bit. But let's get our head around what do we mean by application level. This is a basic diagram just trying to illustrate the life cycle of data between a client, where our application is, and, say, a RDS instance in a cloud provider, say AWS. One place we can encrypt our data is where it's actually stored. And you may have heard of this, and this is called encryption at rest. And this will attack our data. This will protect our data from physical attacks to the underlying storage. But what happens when our data leaves our RDS instance in the cloud? Well, we could encrypt it using a SSL or TLS, and this is known as encryption in transit. But there are a few gaps here where an attacker could get access to our sensitive data. And that could be at the point where it's going from, is that still working? Yeah, it is. There's a few gaps between where it's being decrypted from where it's been in transit to going into our storage and then being encrypted again, so it's encrypted at rest. And then that brings us to application level encryption. And what we mean by that is the client is in control of encrypting and decrypting the data. And what that means is that our sensitive data is encrypted as close to the client as possible and all the way through at all stages of the life cycle, including at any location where that data is stored. And to demonstrate an example of application level encryption and deterministic and non-deterministic encryption, I'll be doing just showing a Rails 7 demo app. So as part of Rails 7, Active Record now supports application level encryption. And there's a few basic steps to set this up. The first step will be to generate some secret keys. Now, these obviously are sensitive keys, but in a prod environment, you'd store these in potentially your Rails credentials files, but for the purposes of this talk, I'm displaying them. They're not used anywhere, so completely fine. And then this is the table that we're going to be using in our demo app. It's a basic users table with an email field. And in our model, what we would do is declare that we want to encrypt our email attribute. So something I prepared earlier to sort of minimize the amount of live coding I had to do. I've got a recording here, and this is creating a user record in our demo Rails app. As we can see, it inserts, but when we try to query that record, we don't get anything returned. And if we look a bit closer, we can see that the value of the email is a ciphertext, and then the value generated when we query is another ciphertext, which is completely different. And this means that we're not able to do a where clause where we can say where this value is equal to another value. And it also limits our ability to do queries such as like our greater than date of birth query. But Active Record has another mode, and it has a deterministic mode which you can switch it over to. And in this example here, we create a record. We can see that the value of the ciphertext is exactly the same as the ciphertext produced when we query the record. Hey, and this seems pretty cool. We get a record back. But every time we create a user record, we're going to get the same ciphertext. And this isn't so great, because potentially if an attacker works out what the plain text value is of that ciphertext, then they could see, and they had access to your database, they'd potentially be able to decipher what the underlying data would be for all instances of that ciphertext. So it seems like non-deterministic is probably the way that we want to go. But how do we make that queryable? This is where order revealing encryption comes in. The research for ORE was conducted by two doctors from Stanford University, Dr. David Wu and Dr. Kevin Louie. And this is a white paper, which is a research paper that was published in 2016. I do not know how to read this paper, but I've been learning about ORE from people that do know how to read this stuff, and been pairing with them as well to learn. So there you go. If you Google ORE, you might see something like this, encryption that reveals the order of its plaintexts. And for me, this isn't really useful. So what we'll do is step through an example of encrypting a plaintext, and we'll keep it really simple. We'll be encrypting just a letter A. But before we go into that, let's discuss what a ORE ciphertext is made up of. So when we encrypt a plaintext value, we get a ORE ciphertext, and that's made up of a left ciphertext and a right ciphertext. And with ORE, what we're able to do is compare the left ciphertext to the right ciphertext and get a result. And that result will be a less than, equal to, or greater than. And what that means, it's telling us that the plain text value of our left ciphertext is either less than, equal to, or greater than the plain text value of our right ciphertext. And in the following example, less than will be represented by -1, equal will be represented by 0, and greater than will be represented by 1. And so this is the life of a plain text in ORE land. And as I mentioned before, we'll be using the letter A. But in this particular land, there's only 4 possible values: 0, 1, 2, and 3. And in cryptography, this is known as a domain, and I'll be referring to the domain as we continue to go through this example. But how does A relate to our values here in the domain? So we have the letters A, B, C, and D. And these are ASCII characters. And under the hood, everything's ones and zeros, right? So we have decimal values for A, B, C, and D. And they're 97, 98, 99, and 100. But we don't have those values available to us. So what we're going to do is convert those to 0, 1, 2, and 3. And how do we encrypt A? So the first part is we have our domain, and it's an ordered domain, so 0, 1, 2, 3, and we have our plain text value. And we start by comparing the value in our domain with our plain text value. And when we get our comparison result, so 0 is equal to 0, so we store a 0. 1 is greater than 0, so we store a 1. And we continue throughout every value in our domain. And we store each result in a set of what we'll call comparison results. And this is the first part that makes up our right ciphertext. We also need to store what's called an offset. And this offset is the location as to where the plain text value and the domain value is equal. And this is the first part that makes up our left ciphertext. So how do all our plain text look with their ORE ciphertexts? And that's what this slide is showing, is that we can see that we have A, B, C, and D, and we've got the comparison results for all the values of that plain text against every value in the domain. And we can see in the left ciphertext, we've got the location of where the left and the right are equal. Say we want to compare C to A. The way that we would do that is we will take the left ciphertext of C, and that gives us a position, offset, or location of 2. And we look in our right ciphertext of A, and we can see that the comparison result is 1. And that's what's returned to us, and that tells us that the left ciphertext is greater than the right ciphertext. There's a bit of a pattern forming here, and we can clearly see what our plain text data is. So let's introduce encryption and keys. In ORE, there are 2 keys, a pseudo-random function key and a pseudo-random permutation key. And these are 2 mathematical concepts that we don't need to dive into today. So for the purposes of this example, we'll call the PRF key a hash key and the PRP key a shuffle key. And what our hash key does is it generates a key to encrypt each comparison result along with an initialization vector. A different key is generated for each encryption and for each comparison result. Now our right ciphertext has another attribute that we're storing, which is the IV that was used in those encryptions. And the shuffle key is then used to shuffle the ordering of our comparison results, providing a bit more misdirection to our ciphertext. We again store the offset in our left ciphertext, but this time it's the new location that our comparison result has been shuffled to. And we also store the key that was used to encrypt that comparison result in our left ciphertext. So our table looked like this before, and now after we've used our shuffle key and our hash key, it's all a bit jumbled up and we've got some new attributes. So we've got our left ciphertext that now has the key and the offset, And we have our right ciphertext that still has our comparison results, but they're a bit jumbled and encrypted, and we have an initialization vector stored in our right ciphertext. And these are the new locations of our comparison results where the left and right ciphertext are equal. So looping back to our diagram of our application and a database, and how does this all fit in, like left and right ciphertexts? And I'm pretty sure like a lot of that might not have landed. It's taken me a while to get my head around how it all works. But the way I'll try to bring it back is how to explain how the left ciphertext and the right ciphertext work together. So what would happen is, say our application wants to query some data. Oh no. It's all right, I had offline mode on slides, so hopefully it's okay. So our client wants to do a query. And so how this works is it uses the shuffle key and the hash key to generate the left ciphertext at the time that it needs to do the query. So we get our left ciphertext with our key and our offset. Meanwhile, over in our database, we've already encrypted all the plain text values that we've got stored there. So we've already got the right ciphertext sitting there in our database. And so all that happens is the left ciphertext is sent in our query. Our database has a function that knows how to compare the left ciphertext to the right ciphertext, and a comparison result is returned. And the cool thing about this is the separation. So the left ciphertext by itself kind of doesn't mean a lot, and also the right ciphertext needs the left ciphertext to work out what the comparison results are. And the other part of this is that the database doesn't need to know anything about the keys. The keys are sitting on the client, and the database can do these comparison results without knowing anything about our keys, which I should have mentioned before are secret. So if you look at our users table from the beginning, with our email, date of birth, and we were able to do our select statement when it was unencrypted, and we encrypted it, and then we couldn't get any records returned. So the way this would look with ORE is we could add another column, our ORE column, with our encrypted right ciphertexts. And when we do our query, instead of querying our date of birth column, we'd point to our ORE column, and our query would include the left ciphertext. And when compared with the right ciphertext, we'd then be able to determine whether the right ciphertext, the plain text value of that right ciphertext, is equal to, less than, or greater than, and we would get a record returned. So again, a lot of that might have not made sense, but please feel free to come chat to me after the talk. The last part here is just doing a demo using a toy ORE library that I've built. We'll go through a bit of the code, and hopefully some of these seem a bit familiar to what we've just spoken about. Here we have the function that actually encrypts. It takes the IV and key and the comparison result. We also have I should call it a method. We have a method that compares the plain texts and returns our -1, 0, and 1. And then also we have a compare ciphertext method, which again takes the IV from the right ciphertext, the key from the left ciphertext, and then the comparison result from the right ciphertext. Our left ciphertext and right ciphertext are represented here by classes. You can see that the left ciphertext is initialized with a offset and key, and there's also a comparison method here which will compare the left ciphertext to the right ciphertext. And our right ciphertext has our initialization vector and our list of comparison results, here called encryptions. And the scheme looks like this. So when we initialize our ORE scheme, we initialize it with a domain size. The default here is 1 byte, so it's a very small domain, obviously larger than what we've just been talking about, but still very, very small. So the potential values in this domain is 8 bits, which is 256 values. And here we have our PRF key, which we referred to as a hash key, and our shuffle key. And then we have an encrypt method. The example that I'll quickly show you is trying to represent what we just went through in the previous slides. So what we do is we initialize our ORE scheme and we provided a domain, and we're going to use that really small domain of 0, 1, 2, and 3. We then create ciphertexts for our values 0, 1, 2, and 3, and what that looks like is something like this. So this is the encryption of 0, which we're saying represented A. We can see that there is a left ciphertext with an offset and a key, and our right ciphertext with the IV and our comparison results. I then stored these ciphertexts in objects for the purposes of this demo. So we just got the letter A, B, C, and D, and then we have an ORE key with a value of that ORE ciphertext. And we can start doing some comparisons. So for this example here, we're comparing the left ciphertext of A to the right ciphertext of D. And we get a -1 returned, which makes sense because A is less than D. And this next example here, we'll be comparing the left ciphertext of D to the right ciphertext of B, and we get the 1, which indicates that D is greater than B. We've been talking about ordering and range queries, so we'll do a quick example of how sorting would work. So here I create an unordered array, and the ordering at the moment is something like this. So we've got D, C, A, B, and we want to put that in order. And so using our sort method here, we take the left ciphertext and we sort that through with the right ciphertext of the next value. I've just added a map here so we can get the output to see what that ordered array looks like, and we can see that now that array is ordered. That's a very simple example, but it was hopefully just trying to show how it all worked under the hood. As I said, oh no, again, what? It's available, it's pushed up, it's available on Ruby Gems, it's toy-ore. There's a bit of documentation there. I probably could add more, but it'll get you started, and there's a lot of comments in the code. I'll tweet the links to my talks, but also they're on my GitHubs. So yeah, the slides are up there on GitHub. The code for toy-ore is there as well. And that's it. Thank you for listening.